Hi everyone, my name is Sophie Sang. Today I have the honor of introducing Professor Alden Griffith. Professor Griffith is an assistant professor of environmental studies at Wellesley College. He received his BA from Wellesley University in 2001 and his PhD in environmental studies from University of California, Santa Cruz in 2008. After that, he moved back to the East Coast, invited by the Wellesley College Botanic Gardens as the Botany Fellow, which was a postdoc position from 2008 to 2011. Professor Griffith is primarily a plant ecologist. His research focuses on invasive species and interactions among plant populations. Beyond the classroom, Professor Griffith has spoken to many different audiences about climate change and issues surrounding science communication. He has served as a distinguished faculty member for the Albright Institute since 2011. This morning, he's with us again to talk about complexity, probability, and uncertainty in a changing climate. Please join me in welcoming our speaker today. Thank you.
Well, good morning. Thank you, Sophie, for that nice introduction. I'm really happy to be here and get to talk to you all today. I love talking to Albright Fellows, and I really enjoy getting an opportunity to talk about these topics, not just topically, but also conceptually, getting into some of the details about how we think about complicated issues. And let me just quickly start with a real broad overview of what I'm going to talk about. The first part of the talk, I'll talk a bit about climate fundamentals, trends in climate, and causes of those trends. Some of this is similar to material that I've presented in previous years, although a lot of it's pretty different. And then the second part of the talk, I really want to focus in on something new in terms of dealing explicitly with uncertainty. How do we deal with it? How do we think about it? How do we deal with complexity? How do we think about things that are happening in the future, potentially the relatively distant future from our perspectives, right? Certainly from political perspectives, very distant future. But I can't obviously talk about climate without talking about the polar vortex and the Arctic blast, because it's freezing. And I started last year's talk in a similar manner, but that involved news articles about record heat in the US and record heat in Australia, et cetera. And I used that last year to make the same point that I'm making this year, that a short-term really weather event is not something that we should look to in terms of thinking about climate. This always brings up ideas and claims about climate, but this is something that's short-term and localized, and by definition, that's not climate, right? In the aggregate, we can look at these things and start to think about, are there trends, what's going on? But just be really careful about things that get sensational headlines as having anything to do with long-term trends, right? And so just, some of you may have explored what's going on behind this, and this has little to do with whether the planet is warming or cooling, and has to do with the weather pattern, and that Arctic air, which it is winter and it's very cold in the Arctic, regardless of whether the planet's warming or not, relatively cold, right? And that air has been sort of funneled down into the US via a really weird jet stream pattern, right? And if we want to look at patterns of short-term variability in terms of both in space and also in time and also localized in space, this is a map that shows the temperature anomaly around the world for December 2013. And this is just an important thing to point out. Anomaly, you're going to see this a lot today. An anomaly is a way of looking at a temperature deviation from an average. It's hard to compare the temperature of the tropics to the temperature of the Arctics because they're so vastly different, but you look at them as a deviation from the average of that particular area, right? And this is, I think, this map relative to 1978 to 1998, so relatively recent averages. And you can see in December, Canada and the US was largely cold. The North Pacific and much of Europe was really, really warm, right? It really depends where you are, when you are. And also, if we're living in the southern hemisphere, and I don't know if anyone was following events down in Argentina, massive heat wave in Argentina at the end of December. And right now in Australia, which I just discovered yesterday, bats are falling dead out of the sky, right? Because it's too hot. So there's, anywhere you look, there's going to be something happening here. And just be very careful about how you interpret it, right? And how you link it to climate. And there's a lot of evidence that significant heat waves and heat records are accumulating at a much faster rate than cold records are. Right? But we're not going to talk about weather. We're talking about climate today. So But I felt like I had to touch upon that because it's something that's tangible. OK, so let's get back to climate. And I want to just do a brief recap so we all know what we're talking about in terms of what climate is and how the climate system sort of at a fundamental level works, right? Earth gets all of its energy, pretty much all of its energy, from the sun, right? And the sun is constantly bathing the Earth in radiant energy and has been doing this for billions of years, right? But the temperature of the Earth has not been going up and up and up and up and up and up for billions of years, right? It's not just like putting something on the stove and watching the temperature climb. It's been, all things considered, relatively stable, plus or minus however many degrees for a very, very long time. And this is because as the Earth has warmed up, it reaches a certain temperature and it radiates energy back out. Just like anything with a temperature does that. You and I are radiating energy because we have a temperature. Right? And at some point, the in and the out comes into balance, and then temperature doesn't change anymore. And that's fundamentally the Earth's energy budget, the ins and outs. Right? And if we do a calculation, this is sort of more or less straightforward physics. If we assume that the Earth is a rock floating in space just by itself, given the distance of the sun and the amount of energy coming from it, it should stabilize to be about 0 degrees Fahrenheit on average, which is not the case. Right? This would be a very, very cold planet. And it's not the case because of greenhouse gases in the atmosphere, naturally occurring greenhouse gases, which are very real and very powerful. And what they do is they absorb some of this infrared radiation that's leaving, and then they re-emit it in all directions. And some of that gets re-emitted back down to Earth. So greenhouse gases effectively trap heat and help bring the temperature up. And the actual average temperature is about 57 degrees Fahrenheit or warmer than would be in the absence of greenhouse gases. So greenhouse gases are very real, very powerful, and very important for the world that we live in, right? Everything that we know about the world wouldn't exist without the real influence of greenhouse gases. So their net effect is to increase downward infrared radiation and trap heat. And the most important greenhouse gas is actually water vapor. Naturally occurring water vapor has a really big impact on the temperature of the planet. But what if we wanted to increase the temperature of the planet by adding a lot of water vapor to the atmosphere? Say we wanted to make it warmer, and we decided to just pump lots of water vapor into the atmosphere. What would happen? What would be the result? Yeah, Diana? Yeah, it would just rain, right? It would come right back out. The atmosphere can only hold so much water, and that depends on the temperature. So water vapor is an important greenhouse gas, but it's also affected by temperature. It's a feedback. It can amplify a change, but you can't cause the planet to change by water vapor. So it's a big player, but it doesn't last in the system very long. On the other hand, carbon dioxide, methane, nitrous oxide, these are just one of, or several of many so-called long-lived greenhouse gases. These are greenhouse gases where if you put them in the atmosphere, they can actually stay there for a while, or their effects are felt for a while, even though all of these go through complex cycles exchanging with the oceans and the land, et cetera. But these are very different from water vapor because you can actually cause something to happen with these greenhouse gases. Okay? All of these are affected by human activity in terms of increasing. We're going to focus mainly on carbon dioxide today, even though these other greenhouse gases are sort of gaining recognition as being, maybe we should think more about those because they might be easier to deal with than carbon dioxide. But carbon dioxide is so intimately tied with human activity, right? And it is because it's the byproduct of the burning of fossil fuels, right? And ever since the start of the Industrial Revolution, which, by and large, sort of in England, with the discovery of vast coal deposits, this carbon dioxide has been emitted into the atmosphere. And it's a very different type of carbon, and that fossil fuels represent carbon that was locked away a long, 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 long time ago. It has not been part of the planet, has not been in the atmosphere for a very long time, hundreds of millions of years. Now we're putting it back in, right? We're taking something completely outside the system. I think you guys talked about systems yesterday, right? So the CO2 from fossil fuels is outside the system. We're now putting it into this dynamic system, right? And so we can look back and see what the level of carbon dioxide has been in the atmosphere. This is a figure going back 400,000 years. We can go back a little further now in good detail, going up to the present, and it's showing the concentration of carbon dioxide in the atmosphere in terms of parts per million, which is amazing. This is a gas measured in parts per million. It has a really important effect on climate. Right? Small amounts can do a lot. And these data are gathered from ice cores from different sources, mainly in Antarctica, but also in Greenland, where they find little ice bubbles trapped in the, or air bubbles trapped in the ice, and they measure the concentration of gases that were trapped in the ice hundreds of thousands of years ago, these little time capsules of the atmosphere. And we see these big cycles of carbon dioxide that correspond extremely well with ice ages. And we know that without carbon dioxide and other greenhouse gases, we can't explain ice ages. And the relationship between greenhouse gases and temperature over ice ages is really complicated. Over long time scales, they affect each other. Carbon dioxide can cause warming, but that also affects how the ocean and organisms in the land release or store carbon dioxide. So there's a lot of interplay over a long period of time, and the relationship isn't as straightforward as we think it is now by injecting tons of carbon dioxide directly into the atmosphere. But let's look what happened ever since we started burning fossil fuels in massive quantities about roughly 200 years ago or so, 250 years ago. Before we did this, the parts per million of CO2 was about 280 in the atmosphere. And today it's 397. It dipped above, or went above 400 last year for the first time. And this yellow line here represents direct observations from Mauna Loa in Hawaii in 1950. So this represents what we've done since 1950, right? It's just a prominent jump up. And as far as we can tell at this level here, about 400, this is probably as high as it's been in about 10 million years or so, right? So we have already done something very radical, right? We're basically conducting an experiment here, seeing what happens. And some people have said this is probably the most radical thing we've ever done, right? And this is really pretty amazing what we're doing to the entire planet here. But what if we go forward here? Well, if we keep on emitting carbon dioxide at this sort of ever-increasing rates along sort of the track that we would expect with fossil fuel energy use, we could double CO2 above pre-industrial by mid-century. And by the end of the century, if we keep on using fossil fuels, there's enough fossil fuels, especially in coal, to take this through the roof of the building, probably, if we wanted to burn it for thousands of years. But by the end of the century, we could easily go above 800 or close to 1,000 if we're really relying on fossil fuels, right? Really radical stuff here. So, oh yeah, actually, I forgot that I had left this in. But this is actually from the same record of ice cores. This is looking at the temperature anomaly in Antarctica. And you see this really, really close correlation. They look at chemical signatures of the ice to determine what the temperature was likely to be, right? And we see this really, really close correlation. And we know that carbon dioxide has played a very important role in the past. All right. So I'm going to start with, is the Earth warming and are we responsible for this warming? My talk in previous years has really focused a lot on this and looked at sort of public perception and the disconnect between what scientists think and what the public think. I'm going to cut completely to the chase here and just give you that basically the consensus among scientists, and this comes from several surveys of both scientists themselves, climate scientists, and in the literature. More than 95% of active climate scientists agree with both of these questions. Right? Usually the numbers comes around to be 97% or so. Right? So this has become what's called the so-called climate consensus. That has to do with warming up till now and the cause of that warming, linking it to human activity. And so the consensus viewpoint here is represented very well by the IPCC, which is the Intergovernmental Panel on Climate Change, which is a UN body. Often the IPCC is portrayed by people who are arguing against climate change that this is some sort of organization that's this government-run conspiracy organization that controls all of scientific research. Important to note that IPCC does not actually do any research. Right? It is a body that helps coordinate research. It's basically a clearinghouse of climate research. It promotes collaboration, synthesis, and communication, and publishes very comprehensive reports of existing research that you could find in peer-reviewed journals in the scientific community. Research is done by thousands of researchers independently in laboratories all around the world. Right? The IPCC has been really critical at helping to collaborate and put people on the same wavelength so that they can make things more comparable and communicating information in a really good way and making it accessible and not buried in journals. But I think it's safe to say that without the IPCC, we probably would know as much as we know about climate now. Right? But they have done a tremendous job at making this accessible. So that's the consensus viewpoint, if you will. There are other viewpoints that represent a much smaller fraction of scientists that are often very vocal, and with a lot of ways to communicate now, it's very easy to find these viewpoints or to put them out there. And I've spent a lot of time, certainly within the last 5 years, looking into the claims of so-called climate skeptics, or those advancing arguments that go against the consensus. And pretty much every time I look into them in detail, these arguments fall apart, or they're unsupported, or they're irrelevant, or a number of different ways in which they don't really counter the consensus. But it's worth looking into again, right? So this is a report that just came out recently, sort of counter to the IPCC. This is the Non-Governmental International Panel on Climate Change, or the NIPCC. And this is, if you look at the authors, it's got a list of people who I recognize as being sort of prominent skeptics who have been holding this viewpoint for a long time. And it bills itself as an authoritative and independent assessment of the latest science concerning the cause and consequences of climate change. NIPCC seeks to objectively analyze and interpret data and facts without conforming to any specific agenda, which is a little weird because it's sponsored by the Heartland Institute, which most definitely has an agenda. For all its reports, NIPCC has worked with leading thinkers in the fields of statistics, physics, economics, geology, climatology, and biology. Right? So this is billing itself as a very comprehensive report, sort of the leading report that goes contrary to the so-called consensus. So let's just take a quick look. This, in their summary for policymakers, this is the what you put out there as your main findings, most important salient points. One figure here, or table really, is the lack of evidence for rising temperatures. And they list these bunch of different data sets here, saying that, well, there's the IPCC one, which shows some warming, but these other ones, they don't show any warming. Right? And if you look closely, they say, well, it's actually between 1942 and 1995 for certain data sets, or between 1979 and 1997 for other data sets. They don't show you the actual data. Maybe they assume you're not going to go look it up. But we can do these things. We can go look at the data. Right? So if we want to look at land surface temperature, can you guys see that okay? This is one data set looking at land surface temperature from temperature stations. And kind of the only way to not see rising temperatures there, well, actually, in this case, this is where they admit that, yes, it's rising a little bit here. Right? This is the 1942 to 1995 trend line here, and they admit that it's rising. If we look at just the United States alone, which is important in terms of impacts and thinking about what might happen here locally, although the US represents about 1.5% of all global surface area, so it's hardly representative of the world. If you look at 1942 to 1995, you can see not really much warming, but that ignores the record-breaking heat that we had last year. This year is probably going to be a bit lower. This doesn't have 2013 on it yet. If we look at sea surface temperature, this is clearly going up. If you want to look at this period here, maybe this indicates that it's not going up, but that's ignoring all the rest of it. If you want to look at satellite data, there's one that I skipped because I don't have access to that data. That's nighttime marine temperature data, but it lines up in papers that I've seen basically exactly the same as sea surface temperature. If we want to look at satellite data, independent ways of looking at temperature, look at the time period that they're looking over, 1979 to 1997. It starts in 1979 because that's when we launched satellites. But this is kind of the only way to say that there's no trend, is if you ignore the rest of it, right? If you look at weather balloons, which aren't really globally comprehensive, but they go back to 1958. I don't know why they still decided we should look at 1979 to 97, because that's the only way you can see that there's no trend. And then they pulled out this paper. It was actually sort of an obscure paper, which I was able to get the data for, which looks at temperature proxies. These are not direct measurements of temperature. These are like looking at chemical signatures of coral or tree rings, things like that indicate temperature. And it goes up only to 1995. But if you look at this period, it's still significant. It's still significantly upward. If you actually go and look at what they say is zero, it's not. Right? So supposedly this report bills itself as the leading thinkers, et cetera. But quite honestly, I would have higher expectations of you guys in my classes in terms of interpreting trends and data. So I'm not going to talk too much about skeptics here, and I don't want to be totally dismissive of it. There's a lot of uncertainty that we'll talk about and a lot of things that we need to understand. But I want you all to be very critical when evaluating claims and really go look into it, okay? When you take the time to do that, and there is a wealth of knowledge out there available to do that, a lot of these really sort of undermine their credibility here. Okay, so let's look at the data in a more objective way here. This is annual global surface temperatures from surface stations as determined by different analyses. And there's another one that I haven't been able to put on here that comes to the same conclusion. If we look at satellite data, which measures something completely different, it's a totally independent way of looking at temperature, we get basically the exact same thing. It's more sensitive to interannual variability, right? But we see this really strong trend going up, particularly since the 1970s, really strong warming trend. And this scale, this is anomalies scale, and so it's sort of, we're talking in maybe a degree or so or less of centigrade, and that doesn't necessarily seem that much. But on a global scale, it's actually really, really substantial. And we'll put that into perspective a little bit later in terms of how much energy we're dealing with here. But something that is worth looking at here is a claim that's come up recently, is if we look, sort of start with 1998 or so, it's maybe the last 17 years of data, there hasn't really been any warming. It's sort of flatlined there, and you could say, well, this is a short time period, but it's bordering on being kind of interesting. 17 years is not super short. But what's going on is really the real question. Is this just a blip, or can we explain it? Why are we not seeing it go up? It's not inconsistent with warming, but it's worth looking at. And some reasons why this is slowed down is likely to do with low solar variability or low solar output during the early part of this period. Also, you guys have probably heard of like La Nina versus El Nino, which it's a big exchange of heat between oceans and land. We've been largely stuck since 2000 or so, largely in a La Nina phase, which is largely a cooling phase. Right? So natural variability explains some of this, but perhaps the best way to look at this is to think about, well, where does global warming go? Like, is the atmosphere all that we care about here? This is what we feel, but is this global warming? Right, so where is global warming going? We know it's going to the atmosphere. We've measured that. Where else do you think it's going? Yeah. Oceans. Right, it could be going to the oceans. Where else might it be going? This thing about energy that's coming in, where could it be going? Yeah. By plants or anything on the land, right? It could be absorbed by the land. Any other place where this energy could be going? Things it could be doing? Yeah?
I mean, I don't know if this is significant or not, but like different photosynthetic and other microbes could be depositing carbon into sediments and things, or like energy. I don't know if that's.
So that's an important part of so-called biogeochemical cycles in terms of how this all feeds back. But just in terms of where this energy comes in and gets either absorbed or reflected or whatnot. So you guys have hit on most of it, like land. Ice is a big one. It goes into melting ice, right? Which takes quite a bit of energy to actually heat up the ice and melt it. Sea ice and ice on land. Where do you think most of this is going? The ocean. The vast majority is going into the ocean. And you guys kind of intuitively know this. When you try and boil water, it takes a lot of energy to raise the temperature of water. It has a really high heat capacity. The vast majority of the energy caused by this imbalance between ingoing and outgoing energy caused by greenhouse gases, or increased greenhouse gases largely, the vast majority is going to the ocean. Right? So if we're basing everything on the atmosphere, we're basically only looking at 2.3% or so of the total warming. It's not really the best sample. So let's look at ocean heat content, which in many respects is sort of the signal of the Earth warming. This is not measured in temperature. This is measured in energy, in joules. 10 to the 22 joules, a huge amount of energy. So this represents a sort of amalgamation of data. It's presented in a 5-year average because going way back, it's really a whole bunch of data sources. And the only way to get good global coverage is to look over long time periods. We can't resolve it very finely going way back. But we can see this trend going up. And this is supposedly where this atmospheric warming is kind of leveled off. The oceans have been increasing at at an even greater rate during this period. And the red line there is newer data that's much more comprehensive, and we can look at finer temporal resolution. Right? So this whole period here, we see huge amounts of warming in the oceans. Right? And this is something that it was not necessarily anticipated that there might be a greater uptake in the oceans. There are subtleties that have importance bearings on climate in terms of where energy goes and how different parts of the climate system interact. Right? And we don't know everything about it. Right? But in terms of accounting where the energy is going, we know that it's increasing still at a dramatic rate. And just to put this into perspective, because I'm sure that 10 to the 21 joules doesn't mean much, if we look at total human energy use between 1998 and 2010, this is data from the World Bank, all the energy that humans used to drive our cars, to heat our buildings, to do everything, it's equivalent to about 1 trillion barrels of oil. During that time period, the amount of energy accumulated in the oceans was about 15 or so times greater than that, which is just kind of mind-boggling that if we wanted to increase the temperature of the oceans and put all of our energy use towards heating the oceans directly by burning fuels and trying to put that heat into the oceans, we wouldn't do nearly as good of a job as the byproduct of burning fuels in terms of the greenhouse gas effect in increasing the energy content of the ocean. And this figure is often translated into something that is kind of mind-boggling, that over this whole time period, every second there's the equivalent of 3.5 Hiroshima-sized atomic bombs going off in the ocean. So it's almost like your entire life. There's like atomic bombs going off in the ocean, increasing the temperature. It's a staggering amount of energy. In the end, it comes down to lots of multiple lines of evidence for warming. Basically, everything that we look at by and large on a global scale over long periods, whether it's physical responses, biological responses, we see the responses that are indicative of warming in the direction of warming. It's really robust. Right? So are we responsible? And this is a big question. If we're going to do something about it, we need to make sure that this has something to do with greenhouse gases. And I'm not going to go into a lot of detail on some of these topics here, so I'm really happy to answer any questions that you guys have either after this or during the week or whenever, and to provide you with some resources and materials to look at this. But there's just sort of too much here to really go into. But I think the best way to approach this is to think about, again, the hallmark of science, which is multiple and independent lines of evidence. We don't trust one thing. Right? We look at lots of things, and one of those things is probably not going to cancel out the other. It all is a body of evidence together. So what are these human fingerprints? One is that we've observed less heat escaping out to space in the wavelengths that we would expect associated with greenhouse gases. Right? And this is difficult to do because there's different technologies from in the 70s to now, but we've observed this. We've observed increased downward greenhouse gas radiation. If there's greenhouse gas radiation warming the planet, you should see increased energy coming down at wavelengths associated with greenhouse gas radiation, and this has also been observed. We see a signature where the lower atmosphere is warming and the upper atmosphere, the stratosphere, is cooling. This sort of seems weird, but this is a physical signature of greenhouse warming. If greenhouse effect is warming the planet, this is what you would expect to see. Whereas if the sun is warming the planet, you would see warming all the way up through the atmosphere, stratosphere too. We see air and oceans gaining heat. This is not just an exchange from oceans to air. This is the whole system is getting warmer. We also do what's called an accounting of radiative forcings. Forcings are the different factors that can affect or cause the temperature to change. Basically, that can cause the energy budget of the planet to become out of balance. So if solar intensity increases, that's a radiative forcing. If we add more greenhouse gases to the atmosphere, that's a radiative forcing. Anything that can cause a change. And so there's been a lot of work trying to account for all of the natural and human anthropogenic factors that could constitute radiative forcings and cause change. And overwhelmingly, the accounting total is that there's a net positive anthropogenic forcing, meaning that there's a net warming attributed, or should be a net warming attributed to human factors. And probably most importantly is there's no plausible natural mechanism for warming of the last 40 years. It's not that there's one thing that controls climate. Lots of things control climate. And earlier on in the century, in the 20th century, the solar activity did increase a little bit, and we see that explains some of the early rise in temperatures. Since then, the sun has been wiggling along like it does and hasn't increased at all, whereas temperatures have shot up. Right? And there's really been no mechanism other than greenhouse warming that has sort of held up under scrutiny. And potentially more importantly, if you flip that around, even if you say, okay, it is the sun or it is this natural factor, you still have to answer the other question of why is the planet not warming because of greenhouse gases? It's hard to counter that in terms of we have really good theoretical reasons why, physical reasons why the planet warms with greenhouse gases. It would be like saying you put a blanket on yourself and somehow you're not getting warmer. So you have to be able to explain both of those. And another tool that we have to look at this is using climate models. And climate models are often sort of used a lot to argue against climate change in terms of sort of holding them to a higher standard than they really are and putting too much importance on them, saying that everything we know about climate change has to do with computer models and it's this black box output. Where in reality, computer models there are many different computer models by many different groups around the world. They have different assumptions. Those assumptions are tested. They're pushed, they're poked, they're prodded to see and understand them, trying to know where they're weak and where they're good. And they're just one tool that we have. And they're certainly not the basis for everything. But we don't have more than one Earth. So if you want to do experiments on the climate, this is the only way you can do it. And we'll look at climate models in a little bit later. But this is the output of dozens of climate models that we're trying to match the observed temperatures of the 20th century. Basically, can we have a climate model that simulates the 20th century temperature grounded in real physics that makes a lot of sense? If you put in all of the influences, including human influences, like greenhouse gases, all of the radiative forcings, it does a pretty good job. Look, if you look here, though, you can actually see this is that dip. The models don't take into account that the oceans are taking up more heat than we expected. Right? So they're not perfect, but they generally explain temperature trends pretty well. If you exclude human influences in these models, you can just get rid of humans and say that we're not putting greenhouse gases into the atmosphere, we're not cutting down forests, we're not doing all these things that influence the climate. These models completely fail to explain the temperature rise of the late 20th century. And this is just one part of the puzzle. This is one line of evidence. Right? Okay. So we've kind of done a quick rapid tour through is the Earth warming and are we responsible, the so-called climate consensus. That kind of brings us up to now. What happens next? This is a big question, obviously, with big policy implications. And I think the best way to think about this is to not address this yet, but to step back and think about how to think of uncertainty, how to deal with complexity, and apply that to such a question. And also to look at these questions that we just visited, is the Earth warming and are we responsible? And really think that, I'll suggest that these are not very good questions at all. They're topically right on, but they're binary yes or no questions. Is the Earth warming? Yes or no, right? And humans tend to love yes or no questions. We like things being black or white, simple, right? If you ever listen to congressional testimony, you'll probably hear just give me a yes or no answer, right? And someone's trying to give a nuanced answer, which isn't apparently good enough, right? So these yes or no answers leave little room for uncertainty, little room for complexity. And they sort of hold science up to a standard that it might not be able to meet, right? Within this framework of yes and no, when does no turn into yes? Right? Like what is this magical line where all of a sudden you say yes? And so that thought experiment just sort of turns this idea of yes or no questions into somewhat of arbitrary questions. These aren't the best way to answer this. We're never 100% certain or 100% not certain. We're somewhere in the middle, right? So what I want to do is spend some time thinking about uncertainty, getting to know uncertainty, not fearing uncertainty. This is how the world works. This is how, if you think about the future, this is how it works. And we have to sort of face it. We have to deal with it, right? So there's a bunch of ways to think of uncertainty. One, within climate change at least, and obviously this applies to anything, it's just ideas of layers of uncertainty. When you have sort of cascading events, uncertainties kind of multiply, they magnify, right? So we can start with what will our greenhouse gas emissions be in the future? That's sort of a first scenario. If we're causing we're causing temperatures to rise from greenhouse gas emissions, well, it all depends on what we do, right? So that's an important part of the future. when trying to make projections? And then how will the climate system respond? That's obviously a big question there. What will be the impacts, right? And uncertainty sort of propagates through this. And within these, there's lots of complicated questions too. What about other human influences on the climate? It's not just greenhouse gases. We put aerosols into the atmosphere that cool the planet. What about future natural influences? Like, we have no idea what the sun is going to do. We really just don't. And by and large, it doesn't tend to go on wild swings and have a huge effect, but it could counter or it could amplify what we're doing, right? Even within how the climate system responds, there's a big cascade of uncertainty in here. This initially starts as an energy imbalance problem. It starts with temperature being forced to go up, right? So how do temperatures respond, which is a very complex question in and of itself. And then from that, how will weather patterns and like precipitation respond to it? That's a whole nother layer below it. Precipitation is notoriously difficult to project. It's much more uncertain than temperatures. And then what will be the impacts? How will ecological and agricultural systems respond? This has huge implications. Which areas are most at risk? And then getting into societal issues, which are hugely involved in thinking about the impacts and the response. What will be the capacity of different nations to respond? And we know this is vastly different. There's huge potential issues of inequality in terms of who's causing this and who's going to bear the burden of it, right? I'm not going to spend too much time today talking about impacts. Happy to point you guys in directions and answer other questions about it later. We just don't have time to open all of this up. But we're going to spend more time on the first part here. So what will our greenhouse gas emissions be in the future? This obviously depends on what we do. And this is where the IPCC serves a really good role in terms of trying to coordinate research and trying to bring researchers together in terms of not picking a million different futures to look at, but pick a set number of scenarios and then run simulations based on those different scenarios so that we can compare them, right? So that it's not apples and oranges. And recently, the most recent IPCC report has basically 4 different scenarios that they're looking at. This is total CO2 emissions, so how much comes out of our smokestacks or tailpipes each year. It's in billion tons of carbon. There's a high emission scenario, which we're more or less tracking. This is sort of the, if we don't do anything and keep on meeting increasing energy needs with fossil fuels, we'll probably be doing something more along the lines of this scenario. So you can maybe call that business as usual. That term gets thrown around a lot, but I think that's sort of a useful one. Then there's the lowest emission scenario, which is really strong mitigation. Let's really change how we get energy and dramatically reduce CO2 emissions. And there's a lot of other factors. There's methane, there's other aerosols in the atmosphere, but this largely sort of tracks those other factors as well. And then these are the resulting CO2 concentrations. So this is how much on an annual basis is going into the atmosphere. This is how much ends up in the atmosphere. Right? And so this is the projection of upwards of maybe 900 parts per million by the end of the century and still accumulating because according to this scenario, we're still pumping tons in every single year. Right? This high mitigation scenario brings us above 400 and stabilizes and starts to bring us back down. And then this is the doubling line. So in the high emission scenario, we might get to a doubling of carbon dioxide around 2050, around mid-century, if we don't do anything. So how will the climate system respond given these different scenarios? How will temperatures respond? How will precipitation respond? We're going to focus more on temperatures sort of as a conceptual model to think about uncertainty here. And there's also there's more certainty there than there is with precipitation. And what I wanted to do before we discuss this, I wanted to show a clip from, this is from a BBC documentary called Science Under Attack. This is Sir Paul Nurse, who is the president of the Royal Society in England, talking about uncertainty. I think he does a really good job describing different types of uncertainty.
In science. But I think it helps to think of uncertainty 2 different sorts of ways. There's uncertainty that often happens at the beginning of a research project when we don't know what's going on. And by testing and doing experiments, things get more and more certain. Knowledge becomes less and less tentative. And there's another sort of uncertainty which is more probabilistic. Like, for example, if we treat somebody for a certain disease, we don't know whether that individual will be cured or not, though we do know probabilistically over 100 individuals that 20 will and 80 won't, for example. And that uncertainty never goes away.
So when I first saw that, I really liked how he characterizes uncertainty in terms of ways in which we might think that uncertainty exists in science, and that science's goal is to just make it smaller and get rid of it, right? Whereas he also recognizes that there just is uncertainty. In some cases, we literally can't get rid of it, right? That a doctor can't tell this particular patient, you're going to die from this disease. Here are the odds, right? Maybe in 200 years, maybe we can do that or something, who knows, right? But over our time scale, we can't reduce it down that much. So here's maybe a way in which a lot of people might think of science in terms of science is really trying to reduce uncertainty. Got all these numbers, we don't know which one it is, we do experiments, we do tests, we're whittling it down, go science, right? And it's 4.5 is the answer, right? So this is sort of like the idea of science is going to get to an answer, right? Which the more you do science and engage in science, you realize that this is really often not how it works. And especially when you're thinking about events in the future, that's a different deal. The idea that we're going to get an exact number is kind of ridiculous. That's not going to happen. There's a lot of reasons why we can't do that. So thinking about things probabilistically is a really useful approach. And honestly, there are scientists, and I'm starting to become one of them, because I do a lot of population modeling in biological systems. And when people do a lot of modeling, they tend to start to think like this. Like you don't think in terms of numbers, like this is a number, right? And what this is a probability distribution. You guys have probably encountered this from exam scores, most likely, right? Like here's the mean, here's the mean, here's the high end, here's the low end. And so you've probably most likely looked at this in hindsight, looking at data that have already come in. Right? But when you're trying to think about data in the future or data that's just unknown, this is a way of kind of probabilistically describing where the actual value is. And we tend to always think about what's the mean, somehow think that that's right. This distribution says that the mean might be the most probable, right? But it could be 8. Totally could be. It's just less likely, right? It's very unlikely to be 10. It's very unlikely to be 0, right? But this is just what it is. Right? So it's important to start thinking about this as a useful representation and not something that is pesky and annoying. Right? That said, it's not that a complete dichotomy because we know everything in one hand or we can't ever reduce uncertainty. Research can absolutely constrain this distribution, can try and reduce uncertainty and bring it in, but probably up to a point in a lot of cases. And there's a lot of research that's been done in certain areas of climate science where we have constrained things a lot. But over the last decade, there has been no more constraining, right? It's just like there are certain things that we can't really pin down that much. There's too much complexity. Other ways of looking at things are that maybe it's not symmetrical, right? Maybe we have an asymmetrical distribution. Like how much you sort of interpret this in terms of like what this implies in terms of what the values might be. Like, what does an asymmetrical distribution mean if you're trying to like interpret what the future value might be? What you can sort of reject or not reject? It's an actual question. So if you're faced with something like this, like what does that mean in terms of you're trying to exclude values? Maybe you could say. Yeah.
It's more probable that you'll get a higher value. It's more probable that you'll get a higher value rather than a lower value since it's skewed to the right.
Right. Well, there's a focus on higher values. I might qualify that a little bit, not say that it's more probable as much. The highest probability is still in the middle, right? This is still where it's most probable. But you're right, it's unlike, you're less likely to be able to exclude these, right? You have more confidence that these can be excluded. You have less confidence that these can be excluded, right? So let's apply this type of thinking to how the climate system might respond. And we'll ask a question, how much will temperatures increase if we double carbon dioxide? And this is just a statement, or this response has become known as climate sensitivity. And this doubling of carbon dioxide bringing the atmospheric total to 560 ppm, that's just sort of a standard by convention reference. In order to ask this question, let's just pick a single value for carbon dioxide and say, what will happen if we do this? Right? That informs us greatly in terms of what will happen if we add more or less, right? But it allows it to be comparable. And over the last few decades, there's been a ton of research looking at this question from lots of different angles, trying to figure out what is the climate sensitivity. How much will temperature increase if we double CO2? Because once we increase temperature, all sorts of feedbacks kick in that amplify or can diminish the initial warming. It's really hard to know what the resulting temperature will be. So here's one example from the literature that shows an asymmetric distribution. Right? That it's pretty easy in this case to exclude really low values. It's harder to exclude higher values. And this type of distribution is somewhat troubling in terms of trying to make predictions, because we'd like to be able to exclude, the worst case scenario potentially. Right? But down here, if the sensitivity is super low, that means that you can add lots of carbon dioxide to the atmosphere and nothing really happens. And in that world, the ice ages don't make sense anymore. Like, we can't explain the past if climate sensitivity is somewhere down here. Right? But there's a huge spread. I mean, look at this. This is not constrained, right? And then this is looking at, the IPCC has, in their previous report, had assembled lots of different probability distributions for climate sensitivity from lots of different independent researchers over the previous few years. And we get lots of different ranges, but there is some general agreement that it's likely within this range. And this is the new IPCC likely range, which is actually down a little bit. It used to be 2 to 4.5. Now it's been widened from 1.5 to 4.5. Right? So we actually increased our uncertainty a little bit in a good way. I'd rather it be low, right? But so this is what we're dealing with here in terms of the most fundamental way in which temperature might respond to greenhouse gases. And with this information, we could make really crude projections in terms of what would the temperature be if we went to 800 parts per million. Having this information, this allows us to sort of make it defines a relationship between the two. But it's not a very good way of doing that. It doesn't give us any information about where things are going to change, what the spatial distribution is going to be. It doesn't give us anything about precipitation or drought. Yeah?
Thank you so much for being here today. I was wondering, you spoke a little bit about differences in the way the sun flares or other factors that could influence the temperature on Earth. And I was wondering is there any way that it would be better for us to have more control over our climate than less control in case something like that were to happen?
Yes, I mean, that's a really vigorous debate going on right now. And I don't want to spend too much time on it, but that generally falls into the realm of what's called geoengineering, which is, can we mitigate climate change by not necessarily getting the root cause of it, which is greenhouse gas emissions, but just doing something to counter it. In that same action could counter something like an increase in solar activity too, right? And the main way to do that, or the main way that's been proposed, is to inject lots of aerosols, tiny little particles, into the stratosphere, which cool the planet by reflecting sunlight. That's what volcanoes temporarily cool the planet. They put lots of stuff right up into the stratosphere and cool it. And so people have floated that idea around. Other people think that's sort of maybe fighting fire with fire. Maybe it's a best worst case scenario. Maybe we shouldn't plan on that because there's lots of other reasons why just carbon dioxide alone, rather than temperature, throws a whole lot of things off whack or out of whack. But it's definitely possible. Theoretically, to counter it by cooling the planet. Yeah.
I guess related to that, is the uncertainty distribution for injecting aerosols into the atmosphere also is it much larger, or do you have a rough estimate of what it looks like? Is it really big? Or?
I think it's probably, I don't really, but I think it's probably pretty constrained in terms of what would be needed to do it, because we've seen we'd have to constantly keep doing it because it eventually rains out. I think we'd be able to figure that out fairly well. I think the biggest uncertainty there is all the other effects. It would be dimming the planet, and it would be applying potentially evenly or not around the globe. So it's more like what are the unintended consequences of that, and what other problems are we ignoring aside from warming by doing that. But I think it's pretty well resolved that, yes, we could do that, and we could probably do it effectively. But it's sort of a whole other can of worms. OK, so I want to take this idea of climate sensitivity and think about doing much more sort of informative representations of what the future climate might look like. And then thinking a little bit about climate models as making projections, not just at looking at the past, but trying to use them to make projections of the future, because really they're the only tool we have to make projections that aren't very crude, that aren't sort of a single blanket, here's what the warming might be. And they've become extremely sophisticated. And, fancier doesn't necessarily imply better. Better is whether they're robust to assumptions, meaning that they give you results that are reliable and that match the previous century and can explain past climates. They're very useful. That's how you evaluate a model. And there's been a lot of critique and changing and comparisons of models. And these models have really come a long way. And they're basically required if we want to investigate spatial patterns and complex phenomena like precipitation. And just to give you a sense of how far they have come in just a few decades is kind of amazing. This is a sort of the state-of-the-art model, one of the models produced in the US, which is showing here modeling surface temperature of the ocean. And these models go down into the ocean, they go up into the atmosphere. They represent everything kind of as cells or blocks. But here's just a simulation of the climate system, and it really represents these incredible eddies very well and captures variability in what's really more associated with weather patterns here, right? But if it's doing this very well, these are the things that also affect where clouds form, where rain forms, right? So it's trying to, from the bottom up, trying to capture these processes, and it's basically at this point kind of the best we have, right? But they're probably never going to get perfect. Probably impossible to do that. So if we have climate models, we have to give them something. We have to give them a scenario. Right? So we can take these different scenarios of CO2 projections. And what I'm going to focus on, not because I want to play up warming and scare everybody, but this is the do nothing scenario, if you will. Right? This is the sort of highest emissions. Yeah.
Hi, my name is Naraini. Thank you for being here.
Mm-hmm.
I have a question about the graph on the left.
Sure.
For a few decades, it shows that the lower emissions line is higher than the medium emissions. I'm just curious why that is.
Yeah, so these different scenarios were developed by different groups, and they sort of assume it's not just an assumption of different emissions, it's kind of an assumption of different futures of how the world will respond that incorporate lots of different socioeconomic factors too, there's sort of a narrative behind these. And honestly, these ones are kind of brand new, and I don't really know exactly why. But there's lots of other things that are varying in here too, in terms of aerosols that are emitted from factories, et cetera. So this isn't the entire deal. This isn't like everything here. And also the way at least I was able to obtain the data, there's a really cool website where you can get these data from, but it's only on every decade or so interval, so it doesn't really resolve a lot of the short-term variability. But I'm not entirely sure. But as you'll see in a little bit, the differences during this period have almost no effect. It's really only when we start to see this big broadening of differences. Yeah.
I have a very similar question. You said you were going to talk about the high emissions graph.
Mm-hmm.
Why does I just noticed that towards the end of the graph, the slope of the high emissions sort of
Levels off.
Levels off.
Uh-huh.
Do you have an explanation for why that happens?
I don't in this scenario, or I don't have an exact one. I would assume that in going forward in 100 years from now, there's probably also going to be so many other technologies that it might be because other technologies are better. It might be because fossil fuels are more expensive. I don't exactly know.
Okay.
For the purposes here, I think we can sort of assume that these are trajectories, and if this world happens to be, that's what that's the resulting effect. But I can make available to you guys. There's a really good guide that explains these different scenarios, because these are sort of the older scenarios were developed in 2000 or so and were used for, or even before that, and were used for a long time. So people got to know those pretty well. These ones are new, and I really don't know exactly what's going on behind them.
Thank you very much.
Yep. All right, so, but assuming that this is sort of, let's keep on burning fossil fuels until there's some compelling reason why we start to level off, but still burn a lot of fossil fuels, let's see what these different models project. And so this is global average surface temperatures, and for each of these different scenarios, there are upwards of, I think, 30 or so different models that are simulating them. Right? And actually, I'm going to show first all of the different trajectories. And so the uncertainty range for the middle scenarios has been left off the graph because otherwise it would just be a big mush and really hard to see. But you can see these are the mean projections by the end of the century from 2081 to 2100. Right? And these are relative to late 20th century temperatures. So this is sort of additional warming. Right? And so even under the scenario where we really strongly mitigate greenhouse gas emissions, we have some continued warming and then level off, right? And hopefully keep it in a range that's not too much of a big deal. With the high emissions scenario, right, we get up into this range that's sort of maybe 2.5 degrees to maybe upwards of 5-something degrees by the end of the century. But I mean, in this case, it's not leveling off, right? We're still putting lots of greenhouse gases into the atmosphere. It still hasn't, the climate has not come to any kind of equilibrium. It's still slowly responding. So let's just focus on this now, not as a single number, because often it's sort of, you'll see numbers presented as there'll be 4 degrees of warming or this or that, but it's just, that's not a really useful way of looking at it. So let's look at this resulting range and sort of turn it sideways and try and think of it now as a probability distribution. Although I should caution that I think a lot of climate scientists don't really like this to be thought of as a probability distribution because these are projections. These are different models, assuming the assumptions of the models, assuming the assumptions for future emissions. And really what we're looking at is a range of model outputs. People don't like to say that models that were near the center are any better than models near the edge. Right? But this still is a description, a probabilistic description of how the models have run based off of 30 different models. None of the models are producing anything down here. None of them are producing anything up here. Right? So this gives us, by the end of the century, this sort of range to deal with here from maybe 2.5 or so to maybe 5 degrees centigrade as sort of our boundaries. And those are really pretty strong differences in terms of warming on a scale that may be more familiar to us, Fahrenheit. Around, at the high end here, around 9 degrees Fahrenheit or so, that's sort of the difference between Boston and something like Atlanta. Really different, right? But it doesn't stop at 2080 to 2100. There's momentum. If we look at the range out to the end of the next century, which is new in the newest IPCC report and the newest models that have been coming out, we see this big widening of the uncertainty range, right? But it starts to incorporate and include some really, really high temperatures. And these temperatures up here are really staggering. This is a vastly different world from where we live in now. And I'll put that in perspective in a second, but I think someone had a hand poking up. No? Okay. But to put this into perspective, we can think about the last time the climate changed significantly, which was coming out of the last ice age, right? Starting around 15,000 years ago or so. And how much do you think temperature rose coming from the ice age to out of the ice age? Anyone have a rough idea of what that was? Geologist in the house?
Do I need a microphone? Maybe just like 2 degrees?
2 degrees Celsius?
Celsius.
Yeah, any others?
I was just reading somewhere that it was between the Ice Age and the interglacial period is about the same as we've seen in the last century here.
No, it's a little more than that. Yeah, we've seen about 1 degree warming centigrade or a little less. And it's hard to constrain. It's estimated to be about between 3 and maybe 7 degrees Celsius. Probably maybe more around like 4 to 5 or so globally, depends where you are on the planet. This is the most, these are the most extreme climate changes that have happened on the planet recently. Excuse me, and it happened over 7,000 years, right? We may do this or more within 100 or 200 years. which is astounding, right? It's 50 times faster than happened in the ice ages. And it's often we think about magnitude just as we tend to think about means, and we don't think about variability as much. We also need to really be thinking about rates, think about how fast something happens. That's often the response. In terms of biological systems, we're often less concerned about exactly what the magnitude is, but it's what's the rate at which it's changing, right? And this is really unprecedented if this were to play out. All right, so given this is sort of the if we do nothing scenario. This is sort of what's on the table, right? How do we respond to this? What do we do? And part of this question is addressed by running different scenarios, by saying here's what happens if we mitigate climate change or mitigate greenhouse gas emissions, right? Trying to propose alternative futures. But when faced with a really complicated and big decision regarding or involving a lot of uncertainty, it might be helpful to sort of flip it around and just say, what kind of mistake do we want to avoid? Right? If we're going to plan for something, if we're going to assume that it's this temperature, we're probably not going to be right. We're not going to be like exactly right. We're probably going to make some mistake one way or the other. And this is one of the reasons why I really like the Schneider and Mastandrea reading that I assigned. They talk about different types of errors very briefly. But have any of you guys come across in classes or readings type 1 and type 2 errors before? Raise your hand. I just want to see. OK, wow, that's actually great. But that's usually sort of stuck in the realm of statistics, and they have this, very difficult to sort of approach title of type 1 and type 2, which is not, it's very statistical. But they're very useful in terms of thinking about how we inherently think about responding to uncertainty and what type of error we don't want to make. So type 1 error, right, would basically be, and if we made a type 1 error, it would be climate change isn't as bad as we thought. We erred on the side of, we said it would be really bad or worse, and it turned out to not be so bad. This is like a so-called false positive. Going to the doctor says you have a disease when you don't have a disease, right? And essentially, a lot of climate skeptics, so they're basically saying that we're making a colossal type 1 error, right? That we're saying there's a big problem when in reality there's no problem. They're sort of turning that into a binary. Type 2 error is climate change is worse than we thought, the false negative. The doctor says you're not sick when you really are sick, right? So what are our outcomes here? The outcome, if we make a type 1 error, the outcome is overreaction, right? That we responded, and it's not going to be free to respond. It's going to involve costs, right? And there's a whole range of what that means. But if we make a type 1 error and we overreact, then maybe we spent a lot of money and we didn't need to do that. Right? The outcome of a type 2 error is that we underreacted. Right? We didn't prepare enough. So to avoid a type 1 error, we could maybe assume a low warming, be really conservative, and say that it's probably not going to warm too much. Right? Well, maybe assume the lower end or something like that. And that would hedge against making a type 1 error. If we want to avoid making a type 2 error, we would assume that it's more on the upper end, right? And assume high warming so that we're sort of prepared for that. Right? And this, obviously, this gets out of the realm of science. This is squarely in the realm of human judgment and human values, right, in terms of what we want to do and how we want to respond. But it helps to sort of remind us all that we're not dealing with specific certainty. We don't know exactly what it's going to be. We can't prepare for exactly what it is. We're probably not going to get it perfectly right. Which way do we want to err on, right? And I think there's kind of as a scientist, I think there's a built-in aversion in scientists to try and avoid type 1 errors. It's sort of the most common thing in statistics and hypothesis testing, that you're advancing a hypothesis against that not being true. Right? So you're making a claim, and your scientists are generally sort of nervous about over-claiming something or going out on the limb. And so this is sort of the essence of scientific conservatism is rooted in not wanting to make a type 1 error. Right? Type 2 errors are really hard in science to even know if they exist. It's very different because it's how do you know if you didn't see something that actually is there? Because you didn't see it, right? It's hard to know. It's not in the data, right? So. But type 2 errors, I think if we think about how we respond to things, we often respond in this way. If you think about, say, you're preparing for a hurricane, what do you prepare for? The worst, right? If the snowstorm that we just recently had, I'm quite certain that the highway departments were preparing for the worst, lest they get chewed out for not being prepared, right? But the real take-home from this is not necessarily what we should or shouldn't do, but that this is a really useful way for trying to evaluate future decisions and being explicit about it, sort of stopping, flipping it inside out and saying, what do we want to avoid, right? So I'm going to end by thinking about sort of what's on the table here and bringing it back to what I cautioned against in the beginning, which is sort of reducing this to like a binary yes or no situation. But ultimately, that's kind of what's going on. The debate and discourse that's happening mainly in the public sphere is it happening, yes or no? And most of the folks saying it's not happening are very adamantly siding on it's absolutely not happening, or it's zero, right? And it kind of comes down to it being a really big bet here. Right? You're making a big bet largely about what's climate sensitivity going to be. Is it going to be high? Is it going to be low? Right? What's the outcome going to be here? But an important thing to think about when you're making a bet is really what's on the table. Right? We've looked at temperatures so far. I just want to look at a few other things in terms of what may happen by the end of the 20th century. This is assuming continued reliance on fossil fuels. We've already seen atmospheric global sea level rise has been so far about only half a foot, although it's already been implicated in potentially more damage from storms due to just slightly higher sea level rise means slightly greater surges, et cetera. Summer Arctic sea ice is probably one of the most dramatic changes that we've seen. Since we've been measuring it in 1979, it's come down by nearly half. And probably even more in terms of volume. We now have really, really thin ice up there that just refreezes on as a thin layer every year. And ocean acidity, which I haven't even talked about, which is huge and has been implicated in some of the mass extinctions going way back in sort of deep time. There's high certainty regarding this. If you increase carbon dioxide in the atmosphere, a lot of that gets absorbed by the oceans, which it already has been doing. It's just physical laws. It happens no matter what. That turns into carbonic acid in the oceans, and it increases the acidity, lowers the pH. It's already happened, increased acidity by 30%. By 2100, we may see atmospheric increase by 200%, a tripling. We may see warming globally between 2.5 to 5 degrees centigrade. In the Arctic, we might see increases upwards of 20 degrees Fahrenheit. That's huge. That's the difference between Fairbanks in Alaska and Chicago. It's like, then this is the high end here, right? But this is what's on the table. This is not, these aren't crazy projections here. These are projections assuming we keep on pumping out lots of fossil fuel emissions. Global sea level rise might be upwards of 3 feet, which is a huge rise with really big implications all over the world, but particularly in low-lying coastal areas, in a lot of places around the world, particularly in Bangladesh. There's huge population living at very low elevation with little capacity, institutional capacity to deal with such problems. By the end of the century, under high emissions, we might see absolutely no Arctic sea ice anymore during the summertime, which is huge and very important habitat up there. And acidity may increase by 150%. So massive changes are on the table here, right? And this is getting far out in terms of this cascading realm of uncertainty. It's really hard to know what is exactly going to happen. But this is sort of as we go up in temperature and get more and more out of sort of the normal realm of this world, what might we see? And these are sort of qualitative, semi-quasi-quantitative assessments of ecological impacts. Corals are already living very close to their thermal tolerance. They're kind of living at the maximum. So it doesn't take much to bring corals above temperatures that they can handle, causing bleaching, causing mortality. There may be species that start to get committed to extinction, even if they're still around. Start getting into higher warming scenarios. The Amazon and other rainforests might not be able to handle the warming and drought pressures that come around 2.5 degrees increase. If we start getting up near 3 degrees, there's kind of no way that we can hope that coral reef systems will be able to survive that. Maybe they can slowly recolonize elsewhere, but they grow slowly, right? This is about the rate. once we start getting up above like 4 degrees, this is really uncharted territories. And I'm not saying these are going to happen, but these are the things that freak ecologists out, because they are looking at the response of how organisms respond to temperatures now and respond to precipitation now, and those are major, major changes, right? Some organisms might really thrive, some might not at all, right? But it's sort of a net lose. Right? The rate at which biodiversity is produced is extremely slow compared to this change, right? So that's a depressing note. But where do we go from here, right? So if it's a big bet, what I really want you to do is apply a really critical lens to this, right? And be skeptical in the true sense of the word skepticism, which is not that you can't be convinced, right? That you are just adamantly against something, but that it's hard to be convinced. And scientists are very skeptical by nature, right? And it has served science as an institution very well to have a lot of skepticism there and a lot of critique, right? So be really critical, and also make sure that you think about how you're thinking, right? And step back and be like, am I reducing this to a binary? Yes, no, and that's not very helpful. How, should I flip things around? Should I step back and look at it in a different way? We tend to always think in implicit ways, and it's really helpful to stop and make that explicit, right? And what's really great about the groups that you guys are working in, you're all coming from different backgrounds, different majors, and you're bringing lots of different viewpoints to the table. So it's a great way to try and get those sort of implicit viewpoints out there and make them explicit and see where you're all coming from. Because some of you may immediately already think in type 1, type 2 errors, right? And without making that explicit, it might not be clear where you're coming from, right? Or some of you may already say, of course we shouldn't think in binary, right? So I don't know if any of you play poker, but usually when you make a bet, you do it based on information, right? And you try your best to know what the other person's got, and you hopefully have good cards, right? We have a ton of information. We've been doing this for decades and decades. We don't have very good cards. This is not a very good bet to make, as far as I'm concerned, that nothing's going to happen if you flood the atmosphere full of greenhouse gases. Maybe we didn't anticipate something. Maybe we'll make a huge type 1 error. Are we willing to put that on the table? Are we willing to make that bet? But we're not making this bet for us. This is a bet we're making, but it's not for us, which makes this such a tricky problem. This is a bet being made for future generations. Right? This is a bet being made for organisms all over the planet. Right? There's literally no organism, maybe tube worms at the bottom of the ocean might not be affected by this, right? But there's every organism on the planet is connected in some way to the climate. Right? So this is a big bet, big question. And I want you guys to consider it very carefully. And I believe I've ended on time with extra time for questions, which is great. So I'm happy to answer any more questions that you guys may have. Yeah.
Hi, my name is Nora. Thank you so much for being here. We talked a lot about the high emissions graph and the continued reliance on fossil fuels. And as an econ major, I'm just asking if are we burning fossil fuels at an increasing rate, or is there like a downward trend?
We have been. I mean, there are dips in it, and like you can see it in the data in terms of the recent recession caused a little bit of a dip. The collapse of the Soviet Union caused a little bit of a dip. But emerging economies in India and China have been increasing it a lot. And I mean, I think a big issue here is it often gets, again, like binary, and it often gets reduced to, is it rich versus the poor, or this or that? And it's important to recognize that like access to energy is really important. Energy and wealth and health are all intricately linked, right? Those countries that have access to more energy also tend to have a lot more wealth and a lot more health, right? And so there's a lot of people who are desperate to have access to more energy, and they should. This is a good thing. We want people coming out of poverty. How we do it is really, really hard. The biggest issue, I mean, in terms of trying to address this as an environmental problem from an economics point of view is within a cost-benefit framework, right? Like a lot of environmental problems, the costs would come immediate. Well, the cost of doing something about it, right, would come immediately, and the benefits of doing something about it would come later. So you have this big disconnect. It makes it really easy to see what might happen now, the cost of implementing something, and really difficult to see, like, what if it turns out to be a type 1 error, right? Then it's a huge waste of money, potentially, right? So it's difficult to weigh those things. Maybe one last thing I'll say about that in terms of cost-benefit is, I don't know if you guys have heard ideas about no regrets scenarios or solutions. And there's a lot of discussion about that, because, again, that's sort of binary. But a no regrets solution would be, let's do something that's good anyhow, right? That even if we have a type 1 error and it turns out to not be a big deal, this was a good thing to do. And within the US, people might advance clean energy within reducing dependence on foreign energy supplies. It's good for our sort of national security anyhow to do that. So that would be sort of a no regrets. There's a lot of debate about that idea, but those things are worth considering in terms of, well, what would we do that might be just good regardless, that still would have a payback as an investment. Don't know if that answered your question. We're a little off track, but okay. Yeah.
So thank you so much for your presentation.
Sure.
My question's slightly off topic, but it was something that I just kept thinking about when you were talking. So women's bodies and our menstrual cycles are connected to the moon and lunar cycles, then that's connected.
You're pushing
to
me way outside
really
of my
outside.
but continue.
But there is a connection. So then how that's connected to the lunar cycle and that's connected to the oceans. So I was just thinking about, like, it blew my mind when you were saying that the heat energy increase in the oceans was equivalent to the rate with the 3.5 Hiroshima bombs per second. Like, so that amount of increase in the oceans, and our bodies are mostly made of water. So I was just wondering, like, maybe what the relationship would be between, like, what kinds of changes have happened in human beings. Like, I feel like that amount of increase in ocean temperature, there couldn't be something without, like, changes in our bodies as well. And I don't know if there's been any research done on that, but it was just interesting to me while you were
sure.
talking.
I mean, I can comment a little bit on that, just in terms of our response would be, like, temperature is always trying to sort of equilibrate itself.
Right.
So, like, heat absorption is different from temperature response. So we're going to be obviously out of equilibrium with our surroundings too, because we make our own warmth, right? And generally have a somewhat constant body temperature. I don't think that would, I mean, the biggest issue with human physiology has usually to do with heat waves, if it's a direct effect of climate. But the overall accumulation of heat in the oceans it's a staggering amount of energy in terms of heat, but it's not a staggering temperature increase. It's a temperature increase that is on par with the atmosphere, right? Because it takes so much energy to bring the oceans up that amount. So I think, and because we don't live in the oceans generally, we're affected indirectly from that, and more about in terms of our immediate environment. But extremes are a big part of the impact, not the mean state. Actually, I do have. I have a million extra slides that we could look at. There we go. This is a report looking at changes in extreme events, because that's often where the problems are. It's not like a little bit warmer. It's like how frequently do really bad things happen. And like heat waves in the last, in 2004 or 3 or so in Europe killed like 50,000 people. It's a big deal. Whether or not that's directly linked to climate change is a big discussion. But we could see means shifting out here, and we start to get more probabilistically more extreme events, right? We could characterize this in terms of shifts in the distribution or spreads in the distribution in terms of how variability happens and how we experience those events. So I think in terms of the response on us directly, it's really more about those extreme events that happen.
Okay.
At least that's what I would think. Yeah.
That's the last question.
Okay.
All right. Thank you again. I thought your analogy about making bets was really fascinating. And I was thinking about how it's hard enough for one government, like the US, to come to a consensus about what it wants to do. But on an international level, it must be very frustrating as a scientist to watch all these nations come together and then negotiations to kind of break down. So I was wondering, as a scientist, what kind of talks you'd like to see on an international level?
That's a really good question. I mean, I think the scientific community is finally recognizing the, the general humanity in the rest of the world, and that these are difficult decisions that aren't just directly informed by science. And so I think the scientific community itself has started to change how to engage, and in part actually become a bit more forthright. There had been a lot, I think scientists are generally reluctant to go out in the public sphere and start talking about this because you're going out on a limb, you're making these claims. How supported are they? Can you get into the details of them? But I think a lot of people are realizing that they feel really good about their data. They are advocates of their data. They believe in it, and they're making claims with their data behind it. So I think you're starting to see more and more scientists get out into the public sphere, and blogs are a really good way of that. And speaking of which, meant to leave you with, these are excellent sites that I really like, especially Skeptical Science is a fantastic site, such a great resource. But there are lots of ways for scientists to communicate now, but at the same time, there's tons of ways, more so than ever, to cause mass confusion and misconceptions about climate change. That was part of my talk from previous years in Albright, is how scientific information gets completely distorted and muddled. I think scientists are starting to do a better job, but I think, actually, within the recent IPCC report, there is an explicit focus on the scientific community putting together scenarios that relate directly to sort of the what if and total carbon budgets, and like how can we relate this scientific information more directly to different adaptation or mitigation scenarios. And the new report, only the first part of it is just out. The adaptation, mitigation, human impacts, all of that hasn't come out yet at all. But that's my understanding, that there's trying to recognize that we like to hold science up as this sort of objective ideal, but this is science that's so fully integrated with society and the real world that we need to make sure that it's not like two very distinct, separate realms. So I think it's being improved, but it's still a long way to go.
So please join me in thanking Professor.